Now, my name is Jules van Lier and I'm head of section sanitary engineering. And I will discuss in this coming lectures on anaerobic technology for wastewater treatment. The lectures will be recorded, so sometimes you see a blank sheet, a blank slide in between, just to make a stop later on, because it will all be recorded in open courseware. So we have a nice synchronization between the slides and the topics, so you can later on nicely look back which topic and the recorded part and the PPT. Okay. Right. Now the lectures are uploaded, at least for today, and for the next week will be uploaded beginning next week. There is also a text chapter uploaded, which is coming from this book, chapter 16, which is dealing on anaerobic wastewater treatment. And the learning objectives that we would like to discuss this morning and next week is that you get an understanding what is anaerobic wastewater treatment, the design, how is the design of the anaerobic reactor systems, so the design based, and what are the potentials for sewage treatment. Now today we will try to stop at about 12, so you will get some lunch here. Since last week we had problems with the license of BioWind to be started, so we have to catch up with that. And at 1:30, my colleague Henry Spanjes will start with the BioWind course on modeling of wastewater treatment systems. Modeling, simulation of wastewater treatment systems. Right. Now, anaerobic digestion, anaerobic treatment, what is it? Anaerobic treatment is digestion is a technology, a biological treatment system, which we stabilize organic matter without the presence of any oxygen. This means that now organic matter in biological wastewater treatment, is it oxidized? If you recall from the other lectures, COD plus oxygen is converted into CO2 or water. Well, in anaerobic systems we don't have any oxygen, so there's no oxygen present to oxidize the carbon and to oxidize all the carbon to CO2. Now, the absence of oxygen means that the carbon itself will be reduced into its final product, into methane gas. And that's one of the basic characteristics of anaerobic treatment, anaerobic digestion. So you produce methane gas from organic matter. It is a reductive conversion process. Like aerobic treatment, it's also a mineralization process, so all the components will be broken down to its pure form. And it's solubilization of organically bound chemicals, so the nutrients will set free as ammonium, phosphate, and sulfides, etc. It's a plain system for wastewater treatment. We know anaerobic digestion also in conjunction with aerobic wastewater treatment for the stabilization of extra sludges. There's no fossil fuel requirement. There's no aeration. Aeration is always brought into a biological tank by force, by pumping, by a compressor. Now that is not needed in anaerobic technology. And it's a system for bioenergy recovery system. And since you produce methane gas is an energy carrier. So in fact you're converting your biomass, your organic mass, into a renewable fuel. Now lately there were some discussions also in the press, there were some doubts about anaerobic digestion technologies. There was one reactor exploded somewhere, and there was a digester that producing methane, but together with some electric spark there was an explosion in the sewage treatment plant at Reactor. Right. The digester, as I mentioned, in conjunction with aerobic treatment, has been used to recover at least some of the energy that you invest in aeration of the biosystems. Here you see a picture, for instance, for a sewage treatment plant of Amsterdam, in the Amsterdam West. You see here, at least in the past, it's now replaced by another one. But anyway, here you see the activated sludge plants, you see the clarifiers, and here you see the digesters. The excess sludge which is coming from the aeration tanks are thickened and digested in the digesters. Methane gas is going generally to a generator, the generator producing electricity, and the electricity is used to feed the compressors. If you make a rough balance over the system, one can say if we enter the activated sludge plant with about 100 kilograms COD, chemical oxygen demand, we need about 100 kilowatt hour of aeration in order to oxidize all the COD into its mineralized products. This is a very efficient system, so the effluent contains 2 to 10, so we have about up to 98% of COD removal efficiency. The bacteria are growing here, and they are converting, in fact, the soluble COD in biological mass. And you can see that about 50% of the soluble components which are present in the wastewater at the start will end up as an excess sludge. So in fact, we're converting soluble pollutants into a sludge pollutant. This is a very energetic reaction, this oxidation reaction, so a lot of energy comes free. And this energy is turned into one part into new sludge and the other part in heat loss. A sewage treatment plant is dilute wastewater, so the heat, it's not really heated up, this sewage treatment plant, because there's not too much COD present in sewage, but you can imagine if you have a concentrated industrial water, then even the reactor will heat it up by this reaction. Now this excess sludge, which is going to the digester, is in fact is also organic matter. It's a pollutant, it's also COD. And one can say that in organic matter, in COD, there's energy is enclosed. Energy is in fact enclosed in the organic matter, which is set when you stabilize the matter, when you turn it into methane gas. So one can calculate that the COD content has an energy content of 13.5 megajoule per kilograms of COD. So this amount is 100 times 13.5 megajoule. Now in this system, part of the COD is converted to sludge. This sludge also contains COD, and one can calculate that the energy content of this sludge is equivalent to 5.7 kilowatt hour theoretically. Now what is deconversion? 1 kilogram in sludge is about 1.5 kilogram COD. That conversion I will explain later on. 1.5 kilogram COD with 13.5 megajoule per kilogram COD, or 3.8 kilowatt hours theoretically, gives you a value of 5.7. Now this amount of energy is then used for aeration. Here we need about 1 kilowatt hour per kilogram for a COD for aeration, and that can be derived in principle from the sludge that you are digesting. So you can make an energy neutral system. However, methane gas needs to be converted into electricity by a generator, and such a generator generally has an efficiency of 35 up to maximum 40%. So not all the energy can be turned into electricity, so you lose some. Now that has been implemented for a long time with aerobic systems. And all large wastewater treatment plants are equipped with a sludge digester in order to recover some of the energy. This is the layout of a commonly applied sewage treatment plant, like here in the Netherlands. The headworks, primary clarifier. Here we have the aeration tank where the fossil energy is needed. Then we have the effluent. And here is a secondary clarifier. And in both clarifiers, excess sludge is in fact settled. It's channeled through a thickener. And in a thickener, the sludge is thickened to a high value, to about 88% or something. Then it is turned into a sludge digester, where the sludge is stabilized. After sludge stabilization, we have a separation. The sludge is with a belt thickener or a centrifuge. We separate the sludge from the water, and the water is going back to the headworks, and the sludge is then going to an incinerator, for instance. At least in the Netherlands, all the sludge is going to an incinerator. Now, we cannot use excess stabilized sludge in agriculture, also we only have the possibility to incinerate it. Now, the interesting part of this is that the energy content, what is coming inside, is about 5 to 6 times the fossil energy requirement in the wastewater treatment plant. Nonetheless, only with the common wastewater treatment plants, only 40% of the fossil energy is covered by sludge, methane gas coming from a sludge digester. So we have a huge energy losses, and the current development in the wastewater treatment plants or with the water boards in the Netherlands is to try to maximize the energy recovery as much as possible in order to close this gap between energy demand and energy recovery. Now, what happens under anaerobic conditions? You can avoid aeration, so you don't have an energy requirement here. There's no need for 100 hours of energy, but you enter the anaerobic reactor with the same amount of COD. Bacteria are converting the COD to its end products. They're producing biogas, and they're producing effluent. The effluent is less pure, so this reaction is less efficient than the aerobic reaction, and the amount of sludge that you produce is also considerably less compared to the aerobic one, about a factor of 10 less sludge. So more of the energy content which is present in the incoming pollutants is going to its end product biogas, and there's a little amount is going to the sludge, and the rest is going to the effluent. This means that the energy which is enclosed in the organic matter is conserved. It's not destructed. If we aerate it, we destruct the energy content because we make CO2. There's no energy anymore in CO2. When there's no oxygen, then the end product will be methane gas. And CO2. And well, this has the energy content, this has no energy content, so the organic matter energy content is channeled from the organic pollutants to the final end product, methane gas. Alright, so this means that there's a huge benefit on energy. Since we don't need aeration, there is no need for aeration. Meanwhile, we have the production of an energy-rich end product. Now, no aeration means for the 100 kilogram COD, it's, we don't need this 100 kilowatt hours of aeration times 3.6, and this 3.6 is megajoule per COD. Here divided by 0.4, which is the energy efficiency of an electricity plant, which is about 40%. So on prime energy we save here 900 megajoule. Then we have methane generation. So 100 kilograms COD is equivalent to about 35 cubic meter of methane, and also that's a stoichiometric calculation we will explain later on. But this amount is equivalent to 13.50 megajoule, or 380 kilowatt hours. Now the 13.50 minus what is in the effluent gives you a certain amount of energy value in the biogas. So the total benefit by implementing an anaerobic reactor technology is about 2000 megajoule per the 100 kilograms of COD. Energy conservation, and that gives you the maximum benefit to implement the anaerobic technology. This treatment technology is developed in the Netherlands in the 70s, and it has particularly been implemented for industrial wastewater treatment, and it has also tried for domestic sewage in our climate conditions, but considering the low concentrations and the low temperature, it is not directly applicable to sewage treatment in the Netherlands. Some difference between aerobic technology and anaerobic technology, so aerobic conversions and anaerobic conversions. I took here a organic compound, glucose, C6H12O6. To stabilize this completely aerobically, we need oxygen, then it's converted into CO2 and water. Under anaerobic conditions, we don't need the oxygen, and the end products, 50% of the carbon is going to CO2, and 50% of the carbon is going to methane. Here we have a lot of energy release. This is a very energetic reaction. And this one is a very modest reaction. Here energy is setting free, so the bacteria can grow on that, but much less in comparison to the aerobic conversion. That's why we have much more sludge produced under aerobic conditions compared to anaerobic conditions. The carbon balance, in this reaction 50% of the carbon is going to the end product, CO2, and 50% of the carbon is going to new mass. In the anaerobic condition, it's 95% of the carbon is going to both methane and CO2. That constitutes both biogas, and 5% is going to the biomass. About the energy balance, 60% of the energy can be found back again in the biomass, and 40% is converted into heat. In the anaerobic condition, 90% is retained in the end product, methane. When you incinerate it, you have if methane is an energy carrier. 5% is in the biomass, and 5% is going to heat production. Because this is a very energetic reaction, the biomass is growing very fast. From the process technology point of view, this is nice. You have a fast growing. But in the end, you result in a sludge that needs to be treated. In the anaerobic conditions, you have a slow growth of biomass, and generally the amount of biomass produced is much less, so much less problems with the sludge. Here we have an input for aeration, so we need aeration systems, compressors and diffusers, and a simple tank without any aeration. So there are quite some difference between aerobic and anaerobic technology. As I mentioned, anaerobic technology started in the Netherlands in the 70s, and that was the reason for that is that under this time the new Surface Law Acts were implemented. That means that all industries needed to treat their wastewater. The polluter pay principle was implemented, so everybody needed to treat the wastewater. But in the meantime, the energy crisis was apparent. The energy was quite expensive in the 70s because of the blockage of Arab countries to the Western countries, and it meant that a lot of industries have meant aerobic technology. And that's why aerobic technology could have been developed, and this development was pretty successful, but it stems from developed indeed started in the 70s. Are there any questions? If there are no questions, I proceed, and I just wait for you to raise your hand. Aerobic conversion processes has been explained by Henry Spanjes in the... Who from you did the fundamental course? You? One? You? Two? Rest not. Right. Okay, so well, in the fundamental course, this process of activated sludge has been explained in all details, and if you convert organic matter in the form of COD, organic matter, by oxygens, the bacteria directly oxidize the organic matter, forming the end product CO2 and water. In the anaerobic conditions, the conversion of organic matter is much more complex. There's a group of, in fact, there's a sequence of several groups of bacteria that are needed to stabilize the organic matter in order to come to the end product. If we start with residues, organic polymers, and even in your green waste bin, you see the organic polymers. If you leave it there, particularly when the temperature is high in summer, you see that after 1 week it starts to stink and it starts to be liquefied. And this, in fact, is the first step of anaerobic conversion process. It's called the hydrolysis. So all the polymers, they are split and chopped in small pieces, and they start to be fermented. And that's also what you smell in the green bin. They start to be fermented to volatile fatty acids. So big polymers are chopped into small pieces. This is called hydrolysis. This is called fermentation of acetogenesis, producing small compounds. Volatile fatty acids, lactate, ethanol. Now then we need another group of bacteria, the acetogenic bacteria, converting these intermediate products into hydrogen, CO2 and acetate. And only in the very last part, another group comes in, it's the methanogenic bacteria, converting the intermediate compounds, hydrogen, CO2, acetate, to methane and CO2. Now these are all different groups of bacteria, and they need to be in balance. They need to share the limited amount of energy which is available during the conversion. So the growth rate of this system, of this group of bacteria, is very low. Right. Now there's a big difference between anaerobic and aerobic conversion. This is relatively simple. One bacteria can go from complex compounds to its mineralized end products. Under anaerobic conditions you have a group of bacteria. You need a group of bacteria in order to come to the end product, methane, CO2. But during all this conversion there is the loss of energy. So the amount of energy which is available here is more or less the same amount which is available here. It's only a change of form of this complex organic matter, simplified organic matter, and this is the most simplified carbon, methane and CO2. But all the energy is contained in the final product. So no loss of energy. Right. Now that has been recognized by industries. And what I mentioned, it was developed in the 70s, 80s in the Netherlands. And it has been implemented now worldwide in many different industries. We made a survey in 2007, and we found about over 2,000 registered high-rate reactors from different companies. The market leaders of technology companies, one is Parks and one is Biothane, here in Delft. Parks is in Friesland. And they constructed, together with some companies from the Netherlands and Japan, over 2,000 registered reactors in this time frame between 75 and 2007. The technology is getting more and more popular in China. When I visited China after 2007, I realized, well, there's about 1,000 reactors available in China, which are not registered, so made by themselves, not. Industries also make their own homemade reactors, help of any consultant company. So the technology itself is pretty well established. There's a huge, particularly in developing countries, but also in the so-called BRIC countries, Brazil, Russia, China, India. And the company Park, for instance, is one of the very successful Dutch companies who is doing business in China. In fact, they have a net cash flow from China to the Netherlands, and there are not many industries at this moment who are able to. So they have an office in an industry in Shanghai, and they implement a lot of these type of systems. Implemented in a huge different amount of industry, and particularly the agro-food industries where we have a lot of organic wastewater. Now, sugar, potato, starch, etc. So the agro-food industries, but also the beverages, the beer, the wineries, etc. Distilleries, pulp and paper, and also chemical industries, and some municipal sewage. But as I mentioned, in the Netherlands, our climate is too cold. But in countries like India and Brazil, also sewage is treated by anaerobic technology. Now that brings us to the benefits of anaerobic pretreatment. It was seen that when you apply anaerobic technology instead of aerobic technology, you have a huge reduction in excess sludge production. This is for the Netherlands very important, since we cannot use sludge in agriculture. We cannot deposit sludge in landfills, so the only thing what we can do with sludge is to incinerate it. And that is quite costly. That costs about 500 euros per ton dry matter. And that is one of the biggest cost factor. Now the fact that you have a 90% sludge reduction, sludge production reduction, means that you have a direct economic benefit. It also leads to the reduction of greenhouse gases. There is no use for fossil fuels, so you save about 1 kilowatt hour per kilogram organic matter. There's no need for aeration. In contrast, you produce energy in the form of methane gas, so you produce about 3.8 kilowatt hours per kilogram organic removed. Now, so you have a double-sided effect. It's a big energy by implementing anaerobic technology. Reactors of using anaerobic technology, they are also very compact. You can load the systems with high loading rates, even up to 5 kilograms COD per cubic meter per day. And that is a loading. If you have a reactor system, you put some cubic meter per hour, and you have some kilogram of COD per cubic meter. Then it depends how much you can convert, how the amount of bacteria that you have, how much you can convert in terms of kilograms of COD per day, or kilograms of COD per cubic meter reactor volume per day. This for aerobic technologies that can be up to 1, 2, 3 kilograms COD per cubic meter per day, and here we see indeed a factor of 10 higher. So reactors are much smaller footprint, and therefore very economic to put at the premises or at adjacent to the industry. Right. The other advantages we will see later on. Okay. Now, what does it mean if you implement an anaerobic treatment plant at the premises of your industry. You can get some carbon credits with when you implement AD project, and the carbon credit is the emission right for CO2. That means if you can save CO2 by producing renewable energy, you can valorize the amount of CO2 that you in fact gain or save. For this calculation, it is compared to a coal-powered electricity plant that emits 0.86 tons CO2 per megawatt hour electric. And the established price for 1 ton of CO2 was 20 euros. Now, this is a real case example. This is a beer brewer. A beer brewer has a very variable flow. Concentrations are much higher than domestic sewage. Domestic sewage is about 400, 500 milligrams COD in average. Here we're talking about 4 grams. Composition fluctuates, temperature fluctuates, pH fluctuates. For modern technologies, the loading capacities of anaerobic wastewater treatment are up to 35. The energy output is 0.5 to 1.7 kilowatt hour per cubic meter of reactor volume installed. And since you're producing renewable energy, you have a CO2 emission reduction. Now, from this flow and the concentration, you can calculate the required reactor volume. And now, well, with this, the flow that we have here, 2 to 5,000, 6,000 cubic meter per day, and this concentration times the concentration gives you a load of COD of 17,000 kilograms per day. Then with a loading capacity of 35 kilograms COD per cubic meter, reactor volume per day gives you a volume of about 500 cubic meters. This means a very small reactor treating this amount of waste. Now, if you would implement aerobic technology with this wastewater, you need at least a volume which is 10 times. The amount of energy and carbon credits, the energy recovered, if you treat 17 tons of COD and you have an efficiency of 80%, the energy content of the methane that you produce is 3,800 kilowatt hours. Then I multiply it by 40% combined heat power efficiency. This means that 70 tons of COD is converted into methane gas with this energy content of methane gas times the efficiency of the electricity plant will give you 1 megawatt of power, or 21 megawatt hour electric. Moreover, this company has no energy consumption, so this amount of COD which is converted anaerobically does not need to be converted aerobically. So the assumed energy requirement of the activated sludge is about 0.5 to 1 kilowatt hour electric per kilogram COD, but you save the 17 tons that are converted anaerobically, so you save another 7 to 40 watt hours. So for this company, the total energy benefit is about 1 million euros per year, which adds in the depreciation of the installation. Now, then you could also sell the carbon credits, because this amount of COD which is turned into alternative fuel, can valorize that with the carbon credits. So a CO2 emission reduction, and this recovered one, 18 tons CO2 per day, that can be valorized and gives you another 150,000 euros per year. And the prevented one cannot be valorized, but the one that you produce as alternative fuel, Meanwhile, for implementing anaerobic technology, therefore you have this direct energy benefit and maybe the carbon credit benefit, which adds up to a very interesting return on investment implementing the wastewater treatment technology. Now that is interesting. That explains also why there's such a high growth, these type of reactor systems in the developing countries, or the interest in China is so big. Now this, for instance, is a project that we worked on in Cuba. This is an alcohol distillery, cane sugar vinasse, making alcohol and of course cane sugar. The wastewater from this type of is very concentrated, and the concentrations, you have to think about over 50 grams of COD per liter, so huge concentrations. With this flow, now that gives you a huge amount of organic matter, soluble organic matter, which is then converted into methane gas, giving a 2.2 megawatt electricity. Now, for this company in Cuba, that means it's in Cuba, so 12 US dollar cents per kilowatt hour, or you're talking about 2 million US dollars. Now that gives them incentives not only to treat wastewater, but to, in fact, to recover the energy, which is then subsequently be used in the industry. The breakthrough of anaerobic technology was in the 75, when in the Netherlands a reactor technology was developed called the upflow anaerobic sludge blanket reactor. In Wageningen University, and this reactor system is a very plain one. Here you see an example. This is in fact an empty tank with a very nice feed distribution, so the wastewater is entering this tank at the bottom of the reactor. The reactor is filled with sludge. There's an upward flow towards the top of the reactor. During passage of the wastewater through the bed of bacteria, the bacteria convert the organic matter into methane gas. Methane gas is bubbling to the top. It's scavenged here by some reverse funnel, some gas separation. Now the gas is separated, and the liquid, which is then free from the gas and also from the solids, is going to the top, and you have a treated effluent. A very simple system, and the main thing, what was observed in this reactor, that the sludges that they aggregate, they form granules, they settle, and if they granulate, then they are more heavy, so you can apply a pretty high upflow velocity, and you don't wash out your bacteria. They all stay inside the reactor, but you have a very compact system with a high upflow. Meanwhile, the biomass retains, so you have an uncoupling of the solids retention time, the time of the bacteria that stay in the reactor, and the hydraulic retention time. Now, more features. There's no electromechanical parts. The footprint is very small, and you form these granular sludges. I think last week was it that Mela discussed about aerobic granular sludge, a new development in domestic sewage. Now, these type of reactors, these methanogenic reactors, they have also granular sludge. Now, the granular sludge stays, because it's quite heavy, stays inside the system, despite the fact you have a very high. Now, this is a blueprint of the reactor developed by the Parks company in the Netherlands, and this is a blueprint of the UASB tech by Biothane in Delft, at Delft site. This is one of the first reactors, 76, sugar factory. Well, to mention it, the system itself is quite plain. You have an empty tank, there's no diffusers, no aeration, you have a nice distribution of feed over the bottom of your... what you would like to achieve is more or less a laminar flow towards upward. It means that you have a very even flow, that all the bacteria are passage, you form the biogas. There's a gas collector in the top. Then you have a because of this gas collector, you create in fact a clarifier at the part of the reactor, and after clarification the water leaves the system at the top. So this is quite turbulent. You have biogas production with a lot of sludge. Here you have a kind of an interceptor where the biogas is entrapped. This means that there is no biogas, there's no turbulence at the top part of the reactor, so all the sludges that come to the top part can settle and slide back to the system. In fact, it's a bioreactor with a secondary clarifier combined. At the bottom you have the bioreactor, and at the top part you have the secondary clarifier. Now, if you have a very concentrated wastewater, then industries recycle sometimes the effluent in order to better mix the incoming effluent in the. Right. Then, now before we start with the design phase of the USB reactor, maybe we make a small break, 10 minutes. Yep. Did we miss somebody? They're outside. Do. Okay, let's proceed. What I would like to discuss now is how you dimension this. You have a wastewater coming in with a certain flow in cubic meter per hour, and you have a concentration of COD, kilogram per cube, which gives you a load, and the load means the amount of waste per time unit, so it's in kilograms of COD per time unit per day. And what is the size of the reactor to treated wastewater? Now, we are dependent on the amount of effect of biomass that we have here in order to convert. The biomass, the bacteria are the biocatalyst. Activated sludge, we have aerobic bacteria, then you need aeration. Here we have anaerobic bacteria, and the anaerobic bacteria, the amount of sludge mass that is able to convert the COD into methane, that determines the volume of reactor that we need. So what we need here is a certain concentration of sludge, the maximum retention of active methanogenic biomass, so the concentration of sludge. And then we also need a certain activity of the sludge. The sludge is the kilogram of COD that can be converted per kilogram of sludge per time unit. The maximum hydraulic loading potential is important, so how quick we can pass the wastewater through the reactor system, but not washing out, not rinsing the biomass from the system. So this hydraulic surface load is important in terms of cubic meter per square meter per hour, or meter per hour, which is called the upflow velocity. The surface load, cubic meter per square meter per hour or meter per hour, this is the upflow velocity. That should be in agreement with the quality of the sludge, so that we don't rinse the sludge, but the sludge is able to settle in the system. The maximum organic loading potential, that is for that we need the activity of the sludge and the concentration. Moreover, the sludge is producing a lot of biogas, and if the turbulence is too high, then we might have a problem in separating the sludge from the water. So also the maximum applicable biogas load in cubic meter per cubic meter biogas per cubic meter reactor volume per day is also a restriction that is determining the volume of the required reactor. Now you can translate a lot of these criteria into upward velocity, surface load, or the cubic meter per hour divided by the surface. Now for most of these type of reactor systems, of the UASB reactor system, the size of the reactor is determined by the admissible loading, the admissible organic loading rate. Now, and that also depends on the composition of the wastewater. Now you can imagine you have a certain concentration of sludge with a certain activity, but if the temperature is low, then the activity is also low. And all biological processes are following a kind of a double Arrhenius curve in temperature. Now what we then plot here is temperature versus the growth rate or versus the conversion rate. Now that follows the temperature curve, Arrhenius curve. This means if we operate a UASB system at a low temperature, likely the volume will be much higher in comparison to a reactor operating at a high temperature, because then we can make use of the conversion capacity of the biomass. So temperature is very important, but also the presence of toxicants. Some of the bacteria may be inhibited by toxicants, so also then you need more space. Nature of the pollutants, the biodegradability of the pollutants. If we feed it with easy biodegradable substrate, then it is also converted in a little amount of time. That the presence of these difficult degradable compounds, so very low biodegradability or slowly biodegradable compounds, require also more time, will also determine the volume. Then what I mentioned, specific methanogenic activity, and of course the sludge concentration. What is also important is the contact between the wastewater and the sludge. You can imagine if you have only a single influent point, then you have a bypass of your sludge. So you need a very nicely even distribution of points in order to bring all the sludge in contact with the incoming wastewater. Now, this means the evenness of a feed distribution that result in a certain contact factor between 0 and 1. And in fact, you can use also the kinetics, the bacterial kinetics, which has been used also for activated sludge, which has been explained in the fundamentals. But okay, you can have a look on Blackboard or an OpenCourseware on that lectures. You can simply base it on a Monod equation. What will be the rate of conversion in dependence to the amount of bacteria that we have, the concentration, the activity of the bacteria, and the contact factor inside a system. That gives you a certain loading rate, and that loading rate, kilograms COD per cubic meter per day. If you know the load incoming from the wastewater, you can calculate the cubic meters of volume of reactor that you need. Now, most simply, particularly for concentrated wastewater, this volume that is dependent on the concentration of the incoming flow times the flow itself, so times the Q, divided by the applicable loading rate. Now, the concentration, kilograms per cube, times cube per hour or day is kilogram per hour and or kilogram per day, and also kilogram per day, divided by the loading capacity in kilograms per cubic meter reactor volume per day will give you the volume. But then, of course, this number has to be known. And that number is a bit of an empirical number. You can calculate it with Monod, like this one. But since it depends, this RV depends on the composition of the wastewater and the temperature and type of substrate to be converted, it is very difficult to calculate it using Monod. And what has been done in the past by the various different wastewaters has been tested using pilot test. What is the applicable loading rate that we can implement with this type of wastewater? Now, when this loading rate is known, the volume can be calculated. On the average, USB reactor has a sludge content of about 35 to 40 kilograms of VSS per cubic meter per day, which is a factor 10 higher compared to activated sludge. In this table you see this RV, this applicable loading rate at various temperatures and with two different types of wastewater. Now, the impact on temperature, on the applicable loading rate is obvious. The higher the temperature, the more or the higher the loading rate that you can apply. But there's also a difference between the composition. Now, this means wastewater with less than 5% suspended solid COD means that this wastewater has a certain amount of organic matter, COD, and only 5% is suspended solids. This wastewater, about 30 to 40% is suspended solids. So this wastewater is much more complex than this wastewater. Meaning, here you need much more conversion steps than with this wastewater. And therefore, the residence time or the loading rate that you can apply with the complicated one is much lower. I give you the example in Cuba of Finasse, very complex wastewater. You need with quite some suspended solids, and you cannot have the same residence time or applicable loading rate in comparison to beer brewing wastewater. So temperature determines, and the complexity of the wastewater determines what is now the exact value of the applicable loading rate, this RV. Also with soluble wastewater, there's a difference in the type of wastewater, a type of compounds that determines the volume. Again, temperature is the determining parameter, but also whether we have a VFA containing wastewater or non-VFA containing wastewater. VFA means volatile fatty acids. And if you recall, the volatile fatty acids are intermediate products If you have organic matter of a lot of polymers, they are converted into monomers. Then they are converted into VFA. And then they are later on converted into methane gas. Now if we feed a wastewater with this, if we feed a reactor with this type of wastewater, then we only make use of a part of the chain, only the last steps, only methanogenesis. So this is very simple wastewater. When we enter the chain here, then the wastewater is more complex, but we also need a bunch of bacteria in order to convert these more complex compounds into VFA. So here we have a bigger group of bacteria required than here. That means that the composition of the sludge with this wastewater is practically only methanogens. And with this wastewater it's not only methanogens but it's also the acidogens and other type of bacteria. So part of the sludge which is inside the reactor is not fully methanogenic. Now that means the applicable loading rates are therefore also lower with the non-VFA wastewater. So the complexity of the wastewater, that will determine the applicable loading rate. If we enter with a methanogenic substrate, we only grow methanogens inside the reactor. When we feed it with a more complex wastewater, we need also other type of bacteria. And if we feed it with suspended solids, then you need also hydrolysis, so the more complex. The more complex the wastewater, the lower the loading rate that you can apply to the system. So organics is rate determining, but also the upward velocity. If the upward velocity is too high, we wash out the sludge from the system and then we lose our capacity. So there's a restriction on the upward velocity that we can implement. So reactor volume based on hydraulic restrictions, now that's very simple. The volume of the reactor is the residence time, hydraulic residence times, times the flow, times the Q. And the maximum upward velocity determines also the height and the surface ratio. According to this relation, so the residence time is the volume of the reactor divided by the Q. The volume is the height times the surface divided by the Q. So there's a relation between the upward velocity and the upward velocity and the minimum surface area of the reactor. So the upward velocity is in fact the flow through the system divided by the surface area. That gives you the meter per hour of upward velocity. Now there are limits. You cannot, if you have this granular sludge that I showed you in the picture, then the settleability is high and you can implement quite a high flow. If you have suspended matter, if you don't have well granulated sludge, then you should lower your upward velocity, otherwise you lose the capacity. Now in dimensioning a reactor, you need to know the flow, the hydraulic, that can be rate limiting, and the organics can be rate limiting. So the flow is determining the volume and the concentration of organic pollutants. This is more or less plot in this slide. What is plotted here is the concentration of pollutants in kilograms of COD per cubic meter. So this is the concentration of the pollutants, kilograms COD per cubic meter. And here is the reactor volume required to treat that flow. Now, if you start at this point, for instance, we have a wastewater with 5 kilograms of COD per cubic meter. Let's say a beer brewer. Beer brewing wastewater is more or less 4 or 5. Now, we have some assumptions. Based on pilot studies, we know that the loading rate, maximum loading rate, is about 15 kilograms COD per cubic meter per day. We have a fixed Q of 250 cubic meter per hour, and we know also that the minimum hydraulic residence time is 4 hours. If we go below that value, then we rinse the sludge and we lose the capacity. So there is a minimum hydraulic retention time, there's a fixed flow, there's a loading capacity, so we can calculate with this concentration the volume. The volume is the concentration times the Q divided by the loading capacity. So this is 5 times 250 divided by 15, which gives you a volume of 2000. This means if you now lower the concentration drops to 4, we immediately require less volume of reactor. Less organics with the same loading capacity, so you can drop down the volume of reactor. Now, you can lower further the concentration of the incoming flow, and directly you will need less and less volume of reactor. Now, you drop down with the volume unless there is a certain amount in which the hydraulics are more important. If you would reduce your reactor volume to a very low volume, lower than the minimum HRT, you will lose the sludge since you're rinsing the sludge from the system. So, despite the fact that you're lowering the concentration of the incoming flow, there is a minimum volume below. You cannot go with the reactor volume, since then the hydraulics are limiting the volume. And so to speak, every anaerobic reactor is therefore determined by 2 calculations in calculating the volume. One is by calculating the volume based on the organic conversion capacity, the volume in relation to the organic conversion capacity, and the other one is the volume in relation to the hydraulics. And this is a minimum HRT, so the volume can drop down, and then we have a fixed lower volume. Yeah?
Are the numbers on the axis, are they fixed, or are they chosen for this design?
Well, no. Well, this is an example, because the example that I gave is 15. If you have more complex wastewater, then you have another type of organic loading potential. So this is a, let's say, hypothetical case, but showing the relation between the organics of the organic limitation and the hydraulic limitation of the reactor volume. This is the same plot, but it gives you insight in what is the impact if we have granular sludge or non-granular sludge. Here again we have a concentration, a pollution strength in kilograms COD per cubic meter, and the volume of the reactor in cubic meter. Now this line is the same as this line. This loading potential of 15 kilograms COD per cubic meter per day. Now if we have a critical upflow velocity of 1.5 meter per hour, when we trespass as we rinse the sludge, so then we get the same line. So we have a minimum volume of 1000. Here the organic loading capacity determines the volume, and here the hydraulic loading capacity, which is the same as this line. Now, what is the impact if we can increase the organic loading capacity? With this concentration of 5 kilograms of COD, with a higher loading rate, we also can apply a lower volume. And if the loading capacity is not 15 but 10, then the volume to treat this concentration of wastewater will be something like 3,000. So depending on the loading capacity that we can implement, you can calculate the volume that you need. What you also see here is two different critical upflow velocity. One critical upflow velocity is 1.5 meter per hour, which is common with flocculant, the lower quality of sludge. But with granular sludge, the upflow velocity can be much higher. And that is interesting. And you see also the impact, what is the impact of granulation of sludge. This loading rate of 15, then the minimum volume is not 1,000, but you can drop down the volume to 250. And then you have a huge reduction in capex, in capital exploitation cost. So the better the quality of the sludge that you have, the granulation, the lower volume you need, in fact, for settling the sludge. And if you recall the lecture of Merle de Kreuk, then she also said, okay, if you have granular sludge, you don't need these big clarifiers anymore. Which is the same in anaerobic reactor technology. If you have granular sludge, you don't need the big reactor volumes in order to retain the sludge, since they settle by itself. Now there's another criterion which is important, is the amount of biogas. You have, particularly with concentrated wastewater, there's a huge amount of turbulence is created. And the biogas upflow velocity can be calculated by the COD concentration times the efficiency of conversion of COD into methane. Let's say 80% is converted into methane. So COD concentration times 80 divided by 100, so times 0.8. Now this is a conversion factor to convert COD in cubic meter of methane, 0.35. And the fraction of methane in the biogas, a correction of temperature, and the upward flow velocity. So this links the biogas upward flow velocity with the liquid upward flow velocity and the amount of COD which is converted. This factor 3.5, this is the conversion of COD and methane gas. If you have this basic equation, CH4, if you oxidize methane, you have 1 mole of methane is equivalent to 2 moles of oxygen, or 2 moles of COD, oxygen demand. 1 mole of methane, if you think volumetrically, then it's 22.4 liter under standard temperature and pressure, which is 2 moles of oxygen, which is 64 grams of COD. Right? Now, and then you can calculate that 1 gram of COD is 22.4 divided by 64 is this 0.35 liter of methane. So this converts, in fact, the mass of COD into the volume of methane gas. Right? Okay, that is this factor 0.35. Now and then, if you design a system, the conventional designed USBs, which are simple reactors with a kind of a reverse funnel, so nothing advanced. Later on, more advanced systems are designed. So 2 to 3 cubic meter of biogas per square meter of surface per hour with this conventional gas liquid solid separators. That is more or less the maximum. And if you have a higher turbulence, then you don't have a nice separation of the sludge from the liquid, and then you have a loose of sludge in the effluent. Okay, so designing volumetrically estimating a USB reactor, so making a rough design sketch, you need to know the concentration of the influent, you need to know the flow, cubic meter per hour, the concentration, kilogram per cubic meter. That gives you a certain COD load. Now then you're going to dimension this in two ways, by the hydraulics, what is the minimum hydraulic retention time, and what is the maximum organic loading capacity. So both calculations will give you a volume, and then the biggest volume you have to take for your design. And you can check then later on the design whether also the biogas is not causing problems in the sludge separation.